This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
All right, we're good to go. All the technology has sorted itself out. Microphone's on. Okay, so on Friday we pushed our way through one worked example on the board, and there were 4 other worked examples in the notes for you to work your way through and test yourself to see whether you can follow the layout, follow the processes. And check to see, obviously, whether you get the right answer, but also whether you are thinking in the right way. It's worth trying them as if it were an exam. It's worth trying them without the guidance first to see, can I pull these ideas from what I've already learned and try to assemble an answer as if I were being tested, and then have a look at how the answer is structured and see whether how your thinking is building up. You do this because you need opportunities to practice, and you need to have opportunity to get it wrong so that you can see where the bits are to get it right. So when you're sitting there wondering how to prepare, how to build up skills, do this stuff. Put everything away, sit down with a blank piece of paper and with a relatively blank question and try it without any guidance and see how far you get. See how far you get towards the numerical answer and how far you get to carefully laying out a thermodynamic type problem. So remember, we spent about half a page of writing stuff down before we even got to solving the problem. And that layout, that format of writing down an analysis, doesn't come by instinct. It doesn't come by magic. It comes by doing it several times until it becomes your normal habit of how you solve the thermodynamic problem. Here I am at my thermo problem. Right. There's my diagram, there's my data, here's my assumptions, here's the principles I'm going to solve it with, and some equations, and here's a statement around what I'm looking for. Now I can begin. At the beginning of last lecture, I hurried my way through a couple of ideas so that you had them available to you as sort of approved tools that you could begin, and I said that very soon, i.e. today, we would go through those in more detail. So we're now going to finish this story of this. We introduced CV, which is the specific volume constant heat, the constant heat at specific volume. And we said that we had a relationship between that and temperature and internal energy. And we went even one step more strongly, which is to say that if I have an ideal gas, I can I can calculate changes in internal energy by knowing the change in temperature and multiplying by the specific heat. So I had U and T connected through CV. Today we're going to connect H and T through CP, but first we need to know what H is. So we'll just spend a little bit of time defining enthalpy and this new letter H. So we'll derive enthalpy and CP, and then we're going to have a closer look at two of our important processes, isothermal and adiabatic, and then we will generalize our analysis through to all processes. Remember, also on Friday I waved my hand to say on ideal gases, they all processes can be mapped to one equation where the power, so it's PV to the power n equals a constant, and n could be anything positive, anything from 0 up to infinity. And the different powers of n indicate different specific processes. So we had a term for isothermal, isochoric, isobaric, adiabatic, and then also that n could be any other number in between. And I said the whole purpose of having these equations is so that we can have analytical solutions to determining the work and the heat transfer during a process. So it's nice that if we can draw a graph of it, we could work out the area under a graph on a PV diagram and say, now I know the heat, now I know the work done. It would be also nice to be able to determine the heat transfer, because those are the two major quantities we're interested in when we're looking at the change between state 1 and state 2. The work and the heat transfer basically define our heat engine, and they allow us to determine our efficiency. So let's get into it. We'll go into an isobaric process. So the CP, when we're doing CV, we held volume constant for the development of the concept of CV. This is not to say that CV can only be used for constant volume process. It was in the definition of the term. We held volume constant while we were defining CV. What we will do for enthalpy is look at a constant pressure process and what happens to its energy as I change volume. And then with that constant pressure process, we'll define CP. So, constant pressure process, flat line on a PV diagram. PV diagram we use because the area underneath it is work. It's one of our friendly property diagrams because it gives us some useful value through the integration of the terms on it. So from state 1 to state 2, we have a change in volume but no change in pressure. And by holding pressure constant, my integration gets easy. I've only got one term changing during this process. And do you remember we took a little bit of time to show that PdV was an integral step, was a differential step of work, which is that piston cylinder example we had. We had pressure acting as a force on an area, and that area had moved a certain distance x. If we combine the idea of the area and the distance x together, we get delta volume. And so the pressure times delta volume was equivalent to the work done by that force acting over that area, acting over that distance. So in our definition of work, due to pushing stuff, through pressure, there's electrical work, spring work, torque work, all these other types. The work due to pushing stuff through pressure, we defined as the differential term as PdV. So if I integrate that from 1 to 2, I have work. And the integral of P, when it's constant, is pretty straightforward. So the integral of, where P is a constant comes out the front, and the integral of dV is V2 minus V1. So I get, for this process, work is the pressure times V2 minus V1, which is the area of this rectangle. It's pretty easy stuff. We begin with a nice easy stuff because it lets the maths be simple while we're defining concepts. Now, what that tells me is that in that process, I don't know, from that graph, I don't know what happened to temperature, but I do know that if I had temperature, I could tell you something about the internal energy. The fact that work was done to get from 1 to 2, if the system is isolated, that energy is in the system now. And I would like a way to be able to account for that as well in just a simple number. I'd like to be able to account for the temperature energy as well as that pressure and volume energy. And so my marker for this, my property for this, we will build up and we will use this idea of enthalpy. And enthalpy is like internal energy. In some situations it's almost the same number in terms of kilojoules per kilogram. But it includes the concept of the energy held by the volume and the pressure on a per kilo basis, the volume and the pressure of the fluid. So what we're going to say, we're going to work our way through to showing that a differential change in heat transfer is equal to my differential change in enthalpy, which is different to saying that a change in temperature equals my change in internal energy. The dq doesn't say necessarily dt. So let's go step by step. We've got our PDV is our dW. A non-flow energy equation, which is the one for a closed boundary. The boundary could be moving, but it's for a closed boundary, so no mass transfer. There's an energy conservation, so it's energy in minus energy out equals change in energy. At the differential form, we had heat transfer in and work out, and the difference between those two gives me the change in the internal energy. So at the differential form, that is dq minus dw equals du. That bit's okay. That's just the same rules we had last week. Nothing's new. I've just said it slightly differently because I'm saying it with a differential, which tells you pretty soon I'm going to integrate. Now, if that's the case, and the only work that gets done is from changing the volume. So this is, remember, this is for my constant pressure process where I just changed my volume a bit. And I said that the work in that process was PDV. What I'm doing here is saying if dW is PDV, and I bring it over this side, I can have an expression for the heat transfer in terms of the change in internal energy and the change in volume at a certain pressure. That's neat, because up until now I didn't have an equation to work out heat transfer. I didn't have a nice one anyways. So in this process, on that PV diagram, I had no information about how the temperature changed. If I've said it's an ideal gas, then you could use the state laws to work out the change in T1 and T2. That doesn't tell you delta Q. It tells you the change in temperature 1 and temperature 2. So we're trying to build up the tools that let us specify the energy transfers, not just the change in properties. So this guy was the work, this guy's the internal energy. And we're going to split that out. That PDV term, to integrate this properly, I'd like to have that written in a form that would integrate nicely. So we take one more step just to make the maths work for me. And this is a step that's the equivalent to adding a 0, but it lets me do my solution easily. What I've done here, PDV and VDP, is given me a term that is the integral of P and V. Sorry, it's the differential of P and V. So in fact, it's probably easiest if I tap that forward just so you see what I'm talking about. If I did dPV, it would be PDV and VDP. Going from here to here, for the problem that I have defined, is the equivalent of adding a 0. Because this guy, what's dP? There is no change in pressure. So this is just here to make my maths neater. I've added a 0 to the term, and it's allowed me to group up and say that dQ is du dPV. And we're taking the extra care. Thermodynamics is a funny little subject where the first time you see it, it kind of makes sense, and the second time you see it, it doesn't make any sense at all. And then you try to teach it, and you think you got it, and then you teach it again, and you didn't quite get it. And you realize there is depth to the math that come from first and second year math, and also comes from advanced maths, that if you break the rules, you get the wrong answer. And so you'll find textbooks being pedantic about some of these definitions. When you say, well, it's not actually changing how I solve my problem when it comes exam time. Why did I spend all that time doing the derivation? There are times when this stuff is important, which means there are times where it's important to have heard at least once that that last step from going from here to here is necessary because the finite changes of finite changes as opposed to infinitesimal changes of delta PV are not necessarily the same as P delta V and V delta P. So we do need to take that extra little care. You may not care, but if I don't put it up there, I haven't done my duty in transmitting this. So, what I'd like to do, internal energy is a nice counter. It's a nice unit. I've got tables of it. I've got a way to approximate it with my CV if I've got an ideal gas, which is to say, if it's a steam problem, I can look it up. If it's an ideal gas problem, once I've got my delta T, I have a way to turn it into delta U. And it's a useful tool for me to count the energy per kilogram due to sensible energy. I'd like to have a new thermoproperty called enthalpy that does the same job but encapsulates that work, that boundary energy, the energy contained in bouncing off the walls. If I do that by saying, let's call it PV, revealing this stuff doesn't feel like a Tuesday morning revelation. If I define my new enthalpy term as U plus PV, I've done something neat, which is my new term. When a new property is defined in terms of other independent properties, then defining the state defines the new property. I'll do that statement again. If I've got the state, if I've got two intensive independent variables, I've got the state pinned down, provided everything's at thermodynamic equilibrium, which means that all its properties can be established. So if I have the state of my fluid, I have its internal energy, and I have its pressure, and I have its specific volume. Those three things, if I add them up into a number, this new number is a property. It's a property defined by the state, which also means that if I have this number and one of those other two, I can work out the rest. So what I've done is to define a new property that has inside it this concept of pressure and specific volume. The reason why that's a neat tool is that now it's something I can tabulate for steam, and now it's something that I can define other tools for calculating, but it gives me an energy marker, a kilojoules per kilogram, to account for this component of energy we didn't previously have. Which is, I tap up and there's all the words that I was about to say. So, that's nice. That's a beginning. We're going to come back to this graph, this isobaric process. All that stuff that I've just done gives me this neat idea that for this process, for the isobaric process, the heat transfer is delta H. So all that hand waving that we just did and all the little shifting things from one side to the other, now I have, because I had dq minus dw equals du, and I took the dw over the other side, and then I developed the idea, we invented the idea of enthalpy. Now I can say that dq can be talked about in terms of the change from one property to another for this isobaric process. That's a neat result, because now I only have to sort, now from state 1 to state 2, by defining the process, I've got my heat transfer. Heat transfer is not an easy thing to measure. States can be determined, and constant pressure process can be determined. So now I have a really interesting tool that can let me work out how much heat was transferred in this process. There's the differential form, which is the first one I wrote down, can also be represented in an integral form. So, With all of that, the steam tables give me everything I need to know about steam. So I don't need any extra tool. Now that I've got the idea of enthalpy, you have a look at the steam tables, there's a column for enthalpy. If I needed to solve a problem that involved enthalpy, I can look it up. If I was given enthalpy, or say I'm halfway through a calculation and I've determined enthalpy, I can use the tables to move around from state to state. I don't have these tables for ideal gases. I've got the equation of state for an ideal gas, and it's nice to have a couple of other rules that are easy to use for an ideal gas. So the one that we came up with on Friday, the one we came up on Wednesday was the CV, the relationship of CV to internal energy and temperature. That's nice because temperature I can measure, internal energy I can't measure. So if I measure temperature 1 and temperature 2, I can tell you how much the internal energy changed for an ideal gas. What I'm doing now is another definition, which is the same kind of concept, but a new variable. So I had CV. I could have called them Jason and Fred. Jason lets me connect temperature and internal energy, and Fred lets me connect enthalpy and temperature. Okay? They just happen to be CV and CP. They're built up through a certain rigor of definitions, but once you've got them, you're free to use them. So once we've got the CV is connects U and T, and we've got CP connects enthalpy and temperature for an ideal gas, you're free to use them in any problem, regardless of whether it's constant volume or constant pressure. So that's my big flag that I'm going to wave around right now, because it comes up time and time and time again. People saying, I wanted to use CP to solve this problem, but I couldn't because it wasn't a constant pressure process. As soon as I say ideal gas, you may use CV and CP as connections between temperature and internal energy and temperature and enthalpy. So, what I want is CP as a relationship between enthalpy and temperature. We'll stick with this isobaric process, which is to say we use CV. For CV, we determined all the properties and all the ideas for a constant volume process. This one we're doing constant pressure process. In the constant volume process, no work was done. In the constant pressure process, a little bit of work is done. But if I consider that to be the only work that was done, because it's a closed system boundary, then what I've got is this statement we had before of dq minus dw equals du. Take the dw over. Actually, I should wave my hands the other way because you're looking at me. dq minus dw equals du. Take the dw over, make it a PV. Now I have dq equals dh. It's a good beginning. If I plug in, if I say this is my definition for the idea of CP, then here I have dq equals cp dt. That's nice. So now I could solve that problem. I could solve the dq problem just by knowing the change in temperature. All right. So, code words in a problem: ideal gas with constant specific heats. So the plural there, constant specific heats, meaning CV is a constant, CP is a constant. Are CV and CP always constant? No. The values for CP and CV can change quite a bit with temperature. So if the problem specifies to you, use constant specific heat, that's great. Use one value for specific heat. There are other options for how do you determine that number for CP or CV. And there's also an entire approach for what happens if I'm covering such a big change in temperature that none of these rules are accurate enough and I need to account for variable specific heat. So we'll get to all of that. If it's an ideal gas, the ideal gas law applies, and so PV can be written as RT. Ideal gas law, PV equals RT. So, if PV can be written as RT, and if U can be written in terms of CV and T, because I've got an ideal gas, if U is CV and T, and PV is R and T, then I can factor out the T and say that H is CV plus R times T. If I accept my definition for CP, that CP is delta, a lot of this seems like I'm just proving the thing that I wrote down to define it. I accept that. If I accept my definition for CP as dHdt, then I have this connection between CP and CV, which are connected through the gas constant for my substance. I find this one of the weirder things in thermo. They're connected because CV and CP and R are all features of the working fluid. How P and V and T are connected through R. Yep, this is the gas constant. So the fact that enthalpy, internal energy, temperature should all be connected, and therefore, so those relationships are connected through CV and CP. So therefore, that there is a connection between CV, CP, and R actually does make sense when you stop and think about it. So, if you were given a problem, for example, that needed CP to solve it, and you weren't told the CP and you weren't given tables to look up CP, but you had CV and R, you can still solve the problem. If you needed R, and you only had the specific heats, you could still solve the problem. This thing is a rule, and it's a nice rule to have in your pile of tools, so that if you're missing something, you say this problem can't be solved. Hopefully you notice that the problem can't be solved without the information, because you're so trained up in using the problems that you're like, yep, no, I absolutely need CP to solve this problem and I don't have it, so it must be here somewhere. That's one of the paths you've got for finding it. A lot of these terms, when we talk about measuring internal energy, when we talk about measuring enthalpy, we talk about giving them some number, because almost everything we're doing is about the delta between one state and another. We have a habit of assigning some arbitrary origin to the number, to the metric. What I've just said is really important, because what it actually says is that if I take the table from one thermo textbook and the table from another thermo textbook, I shouldn't expect them to have the same number values in the tables. It's nice if they do. There's no reason why they would. This textbook, this table, might have used a different reference origin for their numbers than this guy. So I can't cross over between two sources. Internally, all the tables are consistent. Internally, all the tables are consistent. The delta between two states will be the same, because that's how the rules work. All that's happened is the numbers, the absolute values of the numbers look different because they've chosen a different origin. They might have chosen normal temperature and pressure instead of standard temperature and pressure as their origin. They might have chosen negative 273.14 as their origin. Different textbooks will do that, so you can't swap between table sources. But once you're in a table set, they should be all self-consistent, and also the delta between state 1 and state 2 should be consistent. So all the different ways that can be written for enthalpy. We've got of all those ways, these are the two most important ones. Remember, we've got lowercase letters are for the specific values, and uppercase letters are for the total values. So the total delta H, you need the mass term in there. These are written down for ideal gas, or a perfect gas. All right. Before I click on, that's more words than I used on Friday. On Friday, I waved my hand and said these ideas exist, and now we spent a bit more time in the maths and derivation of them. Is there anything there that just didn't make sense? Yeah.
I have a question, not that does it make sense, but you said we assume that in the CV there is assumption that B's constant?
To define, to allow us to define the term CV, we used the example of a constant volume process. And once we had defined CV and been happy that it connects T and U, then it can be used as any time that I have an ideal gas problem.
Even if it's not constant?
Even if it's, I would say this absolutely outright. Absolutely, absolutely, absolutely. When I say ideal gas, I can use CV and CP whenever I want when I say ideal gas. Okay, this is important because this, it was only last year that I realised that that doesn't come through very clearly, and that was because someone asked me this question after a lecture, and it hadn't occurred to me that I hadn't said this out loud. In the derivation for the idea, we choose one process to make our derivation clear and easy to follow. We get this derivation for CV, and it obeys some rules. CV connects, this is just the key thing out of all of this. CV for an ideal gas connects internal energy and temperature. CP for an ideal gas connects enthalpy and temperature. Once I tell you you've got an ideal gas, you may use CP and CV and delta T to solve internal energy and enthalpy deltas. You may use internal energy and enthalpy to solve for finding temperature. So, ideal gas running through a turbine, and I ask you what the temperature of the exit is. You use enthalpy changes to get there, and once you've got the enthalpy of the exit, you can then find temperature. Or you say, I know the work done and the heat transfer, I have enough information to work out the delta energy, delta H, CP delta T, now I've got my T. That was not a constant pressure or a constant temperature or a constant volume process. But because I said ideal gas, I can use CP delta T and CV delta T. This is just super important. Yep.
I don't think I understood exactly how work and enthalpy are related.
So there's a concept of work that we refer to as boundary work, which is the work done in changing a volume of something and it incorporates constant or changing pressure. So all the energy contained in shifting boundaries is called boundary work. Boundary work is a PDV term, or is a delta PV term. If I define enthalpy as a property that encapsulates sensible as well as pressure energy, then I can take that, I'm going to see if I can wave the right way, I'm going to take that boundary work, plop it over the other side, I can define it in terms of properties, which means I don't need to know the process. P and specific volume are properties. So now I can create, rather than keeping track of all the P's and the V's and making you look up 3 different properties on the table, we group it into one number to make our life easy. And that only is allowed to happen for the boundary work. Now we'll do a bit more with that when we come to flow processes. Enthalpy, internal energy gets used in closed stuff, and enthalpy gets used in flow processes. That's sort of the other big split in my toolbox. And that's because in the flow process, I'm at the inlet and the outlet, I'm trying to squeeze a certain volume into the boundary, into the system boundary, and I'm allowing a certain volume out of the system boundary at a pressure. And I want to account for that energy. It took some energy to push in, and it releases some energy to release out. I wrap that up into enthalpy, and I use enthalpy to solve my problem for tracking the energy. All the other forms of work stay on this side of the equation. So the fact that the turbine produces work, that turbine work stays over here. So the DQ and the turbine work are over here. The boundary work for pushing fluid in and out of the system comes over in my enthalpy term. And we'll do that like 2 or 3 more times to help lock it in. Okay, we keep going. We're going to look at now with these new tools that we've armed ourselves. The activities we're undertaking now are to do some analytical solutions for isothermal processes and adiabatic processes. Analytical solutions are nice because I don't need to simulate the flow, I don't need to simulate the process. I can actually get an exact number for, importantly, the work done and the heat transfer. Those are the 2 major quantities I care about when I'm designing a thermodynamic system. So, isothermal process. Isothermal is constant temperature, which means if I write it on a PV graph, I don't get a straight line, I get a hyperbola, if it's an ideal gas. That line up there doesn't say whether it's an ideal gas or not. It's just saying work is equal to the space under the line. So there's nothing new yet, there's no assumptions. And what I'm going to do is wander my way through the isothermal ideal gas equation. So the ideal gas equation, PV equals RT. If T is a constant, it means PV is a constant. Okay? Oh, there you go. When you've been saying the same stuff for a while. So, what we've got then is for a general substance, if we know state 1 and state 2, delta U can come from a table. That's nice. And then if I know Q or W, I can work out the thing that I don't have. That's for a table, for a general substance. And so I could also determine work if I had the process marked on a graph, because just numerically integrating, which is to say colour in the squares under the line, or do whatever tool you want to work out the area of a graph, I could do that. But with ideal gases, I can actually analytically solve it. I don't need to look up all the properties of a table. I don't need to do a numerical integration from properties on a table. I have a relationship of PV equals RT. And so with T constant, I get PV as a constant. That's nice. And that's a hyperbolic on the graph. Now then I magically put up, ta-da, the integral of a hyperbola. So what just happened there? Let's see how good my ability to integrate on screen is. PV is a constant, and work is the integral of PDV. The previous time we did this integral was easy because P was a constant, so the P came out of the integral. P is not a constant, and P now is not independent of V, so P needs to be written in terms of V. If I'm going to do this integral, actually really do it, I can't just leave my P there. I need to change it for something in terms of V. So, if this guy is the case, then I substitute in something for P. What do I substitute in? This constant is RT, yeah? I want to replace that, and so what I get is RT on, is that on the screen? No. I'm trouble with zooming in. This constant was RT, PV equals RT, because I'm an ideal gas. As a consequence, I can write P in terms of V. R is a constant, T is a constant. This is a nice thing. If I put this into my integral, I get the integral of RT on V, dV. We're doing pretty well so far. This guy is a constant, comes out of the integral. RT integral 1 on V. I said before that it was important for us to remember the only tricky integral that we come across is the integral of 1 on x. And the integral of 1 on x is what? Okay, I've got two people saying log x and most people going, please don't look at me, please don't look at me, please don't look at me. Okay. The integral of 1 on x is log. And so if I'm doing an integral from 1 to 2, what I get is RT log V2 on V1. If you can't do this last step, you know what? I'm feeling nice today. RT log laws say that when you're doing the log of V2 and the log of V1, they end up being the ratio V2 over V1. I do that hand holding because I don't want you to ever get it wrong, and I don't want to keep seeing it got wrong in the exam. And you're looking at it going, why on earth is he showing me a log? I did this in year 12. I'm showing it because for somehow magically you get to the exam and you don't know it anymore. Please don't be afraid of integral signs. Please be aware that you can do this. The most important thing that got told to me in my undergrad years when I was sitting there staring at an integral sign. And it seems like a weird moment in life for someone to sit next to you and go, it's just an integral. You can do this. The integral sign tends to shut people's brains down, and I don't know why. You're waiting for someone to give you the answer because for some reason they look tricky. Now, maths is not hard, and you can do this. So let's get back on screen. That's my little pep talk. Yes, you can. All right. It's also important when you hit fluids, when everything gets much, much harder. So, at Joule's law, we said that if delta T equals 0, delta U is 0. And if delta U is C delta T, then what we've got there is that Q equals W equals RT log V2 and V1. Okay. This guy is nice because what I now have is a statement for heat transfer and a statement for work in terms of properties. I've said it was an ideal gas, and at the moment that I said it's ideal gas isothermal, I have an analytical answer for my heat transfer and my work done. That's neat. Let's play the same game with an adiabatic process. Adiabatic means there's no heat transfer, which means I have an analytical statement for the heat transfer. Analytical solution for the heat transfer in an adiabatic process is Q equals 0. Nice. So, the adiabatic process equation, if you remember me waving, I said polytropic processes, PV to the power something equals a constant. The adiabatic version of that was PV to the power gamma. So that's what we're aiming for. PV to the gamma is a constant. So here we go. We've got starting always in the same place. These are just energy balance equations. It's the only tool we've learned. dq is 0, so I've got dw equals du. dw comes around the other side because I've only got boundary work. I've only got the change in the volume work. And I've just given myself a nice happy definition of dH. So what I've got is dH equals 0, which means that H1 equals H2. So dq equals 0. If I write du as CV dt and write dw as PdV, I get PdV and CV dt. If I say these letters fast enough, you will have no idea what I've just said. And then when you look up, you see a new equation on the board. You're like, I don't even know where that came from. This is du and dw equals 0 because there's no heat transfer. I've said ideal gas, so I am allowed to use CV dt. This guy is my boundary work, PdV, but P is not independent of V. So let's get deeper into it. What I'm going to do to crack this problem is to differentiate the ideal gas equation. PV equals RT. And that's my goal. I'll leave my goal up on screen so you know where we're even heading. Differentiate the perfect gas equation. I've got R dt equals P dV. Remember, P is not independent of V, so that differential needs to be the total differential of PV. And if I split that out, I get the PdV and the VdP. Now this time I don't have a magic trick of saying dP was 0 and so I can get rid of a term. I actually need both of those. What I want to do is start getting rid of stuff. PdV is okay. My PdV and my VdPs, they're okay because they're in terms of properties. It's the dt that I want to get rid of. And so what I'm going to do is substitute in my dt, which is to say, here, I'm going to replace this guy with this, and my CV and my relationship between CV and T, and eventually, quite quickly, I get CV on R, PDV, PDV, VDP. Like I said, if I say them all too fast, what's happened is I've plugged in a value here for dt in terms of CV. And then if I multiply through by R everywhere, now remember one side of this equation is 0, and so multiplying through by R is easy. And then I group everything up. What I have, this stuff, it's neater for me to tap through it. It is important for you to try to walk your way through it. I pause and speak like that because this grouping up, you need to keep track of your CV, you need to keep track of your R, and you want to group up all your PDV terms. So there's a PDV term out here which was multiplied by R. So this guy was a CV, this guy was an R, and this guy, because it's CV times this CV stays over here. You with me? So we'll do that again. Multiply through by R. There's an R here and no R here. R PDV and CV PDV, I've grouped them together. And CV VDP is over here. So what next? Because I've got a connection between CP and CV and R, I'm going to divide through by PV and see what happens then. Now, why would I be bothering with this kind of idea? My goal was to validate the PV gamma, and I don't know if you remember when we introduced the idea of gamma, we said the gamma was CP on CV. So at some point I want to be using the fact that R exists to generate a gamma somewhere in this equation. So at some point when I integrate, I'm going to need a gamma popping out over my V. So that's what's going on. I'm replacing my R with the CP-CV terms, and in they go, in they go. Divide through by PV, divide this through by PV, divide this through by PV, and I end up with 1 on V, 1 on P. So now, this last step is actually pretty important in terms of being able to solve the problem. This guy, oh wow, I'm too close to the microphone, sorry. This guy is our log integral. This guy is our log integral when we finally get around to doing the integration. This guy, CP on CV, is the gamma I was hunting for. And that's come from replacing R with CV, with CP, CP and CV, and then getting rid of, sorry, divide, I think I was saying divide by PDV, divide by PV. I've done the division by PV here so that I can turn this into a differential in terms only of V, and so that I can turn this in terms of an integral in terms of only P, which is what's happened here and here. The other side was 0, so it doesn't matter that I divided through by PV. Gamma is CP on CV, and I do my integral. I've got one nice integral that's a log and another nice integral that's a log. So I've got CP CV log V and log P equals some constant. I integrated, and so it doesn't equal 0 anymore, it equals a constant. If I put those logs together, and I pay careful attention, if this is gamma, this is the same as log V to the gamma. Adding two logs is the same as the log of the multiple of those two. So this statement here is P times V to the gamma equals some constant, and that was the adiabatic relationship. So a while ago we said if I have an adiabatic process, it's represented by PV to the gamma. What we've now done is the math derivation to show that that's fine. We've shown it for an ideal gas. That statement is only okay for an ideal gas. Once I said it was an ideal gas, I could use CP, I could use CV, and I could use the ideal gas law to do my integrals and come up with an analytical solution. So what? My objective with the isothermal process was to come up with a statement for heat transfer and work. the adiabatic process, I already have my statement for heat transfer, which is 0. I still don't have my statement for work. And so what I'd like to do next is come up with a statement for work. But we'll come to that in just a moment. I'm going to play with this gamma idea, this adiabatic index. For many of the gases we deal with, you will see a number 1.4 or 5 over 3. Things like helium, neon, argon, xenon. Sorry, 5 is not 1.4, my apologies, 1.6. For diatomic gases, oxygen, nitrogen are air, so we also get the same thing. We get 1.4. Polyatomic gases, now you're not required to memorize this. You're required to know that gamma can be different for different working fluids. It's actually really important if you're looking up alternative ways of producing efficient energy and you see people talking about CO2 cycles. The difference between air gamma and CO2 gamma makes a massive difference in the maximum possible efficiency out of a gas turbine running on air as the fluid running through it, as opposed to carbon dioxide as the fluid running through it. It's a small change in a number that unleashes a big potential. Little bits of maths, understand it deeply enough, you can unlock future energy. Neat trick for a Tuesday. Okay. I didn't put up the work example because we'll get there shortly. Because what I'm actually going to do is the everything equation. The everything equation for a polytropic process. If all ideal gas processes can be summarized by a polytropic process, PV to the n, maybe I can use that PV to the n in all my integrals, and then when I know n, I can substitute whatever the appropriate n was. Maybe it magically pops out. And the answer is yes, it does, except for the case where n equals 1. What's the case where n equals 1? Isothermal? Isothermal. So where n equals 1, PV equals a constant, that's your isothermal ideal gas relationship. That's the only one where this breaks down. So we'll define heat transfer and work for a polytropic process because that's my one equation. That's all I need. Except for this one case, and we've already done the one case. We already determined a statement for work for an isothermal process, so we've got that tucked away. Everything else we can solve at a generic basis. So those are the things I put up on Friday, and I'll just remind them if you weren't watching on Friday. I haven't had a chance to review the lecture yet. For an ideal gas, they can be represented as PV to the something. If the something is 0, we get isobaric. If the something is 1, we get isothermal. If the something is infinity, through the magic of maths of things raised to the power infinity, we get an isochoric process, which is to say V equals a constant, and P disappears. And if it were gamma, we get an adiabatic process, no heat transfer. And so what we're going to do is plug those in to our integral and do the generic integral, which means that for all ideal gas processes, there is one nice equation for the work done and one nice equation for the heat transfer. I need to get a wriggle on because there's 3 pages and 3 minutes. And it's a little bit rude for me to tap through many derivations. So what I'm going to do is get them up on screen and we can talk through them. I'm going to get the work one up on screen and we can talk through it, and then I'll get the heat transfer one up on screen. The work one. This is done with K instead of gamma. Read this as gamma, read this as gamma. If I had PV to the gamma, PV to the n, sorry, this is not gamma. This is a constant. This is a constant. This is PV to the n is a constant, and I'm calling the constant K. If I put PV to the n, and I just substitute in so that I've just got an integral in terms of V, 1 over V to the n is actually a nice integral. I don't need to do any logs. What I get is n minus 1, V to the n minus 1 when I do my integral. This is the same as the integral of x to the minus n. Yep, you can do that one. Provided nx does not equal 1, and then that integral I can actually plug in, I can solve, and I can put back in p's and v's. And what I end up with is p1 v1 p1 p minus p2 v2 over n minus 1. And we do know k is r. so when I get that all into here, what I have is that work is r on n minus 1, where n was whatever the polytropic constant was, times the delta T. Absorb, digest, we can discuss later, because I want to get the heat transfer equation up on screen, and there's more derivation there. Hooray, look, 1 minute's worth of derivation. I'm happy to go back through this with anyone who wants to understand it more deeply.